Hello everyone, here's another Physics 30 Alberta Diploma released question from 2009. Actually, this is two questions, MC8 and MC9. We have three charged spheres. We're told that a student has three identical spheres labeled K, L, and M. They're on insulated stands and equally spaced, as shown below. Charges on the spheres are +3, -5, and +2. And we're told that the charges are just algebra, basically. So we're told 3x, -5x, and 2x. Okay, so first question, question 8. We need to know the direction of the net electric force on sphere L due to spheres K and M. Okay, so we're asked, what direction is the force acting on L as a result of K and M? Okay, so to get into this, we're going to think about these charges. Okay, so here they are. And of course, whenever we're looking at the force electric, we're dealing with Coulomb's law, K, which is a constant, multiplied by the two charges involved, divided by the distance between the charges squared. So let's just abbreviate this. We're not going to be doing any calculations. Abbreviating it to just a proportion. So the force electric is proportional essentially to the two charges, Q and Q. So we're ignoring K because we're not making a calculation. We're also going to ignore R because the R is the same for between K and L. In other words, this R is the same as this R. So the distances are equal, so we're not interested in that. What's going to have an effect on the force is simply the charges. Okay, so let's go ahead and just think about this with regards to QK, in other words, the charge of K and the charge of L. Well, charge K is 3x, so we're just going to call it 3. And of course, when we're dealing with force electric and charge, we're not interested in the positive or the negative. It's a scalar value, so there is no direction with regards to that positive or negative. So we're just going to call it 3. And L, of course, is 5. So 3 times 5. So it's going to give us a magnitude. And again, we're not really interested in the actual value in newtons. We're just looking at the proportionality. So of course, 3 times 5 is 15. So that's going to give us the force acting on L as a result of K and L's charges. So that's this force here. This is the force coming, it's the force electric from K and L. Okay, now we're going to take a look at the force, the proportionality of the force electric between charge M and charge L. Well, charge M is 2, +2, but again, we're not interested in the positive or negative. And again, charge L is 5, so 2 times 5 is 10. So hopefully you can see that this force here, this vector arrow, is going to be smaller. The force electric between M and L is smaller than the force electric between K and L. So the net force is the sum of these two forces. If I was to draw these two vectors tail to tip, we would see that there would be a resultant going to the left, small resultant to the left. And so that tells us the answer. We can say that the direction of the net electric force on sphere L due to spheres K and M is to the left of the page. So in this case, the answer must be must be A. So for question 9, MC9, now we're going to be thinking about this P point, this hypothetical point, directly above L, and we're asked for the direction of the net electric field, and it's asking it's mostly to the left, to the right, top or bottom. So we need to think about the field lines. Okay, well, hopefully you can remember field lines are going to move away just by convention. We draw them pointing away from a positive charge. So let's just highlight the positives and negatives. Okay, so QK is a positive, QM is a positive, but QL is a negative. So let's go ahead and draw these on. Now, if I was only looking at sphere K in isolation, of course, what I would be doing is drawing my arrows going away. So here they are. We've got one arrow going this way, and it'll be pointing away in all directions. Of course, the amount of these arrows we would call flux, but we don't need to worry about that. Now I'm going to pause there because like I said, if this sphere was in isolation, I would just keep doing these all the way around. However, because sphere L here has a negative charge, hopefully you can remember that with a negative charge, the field lines go towards the negative charge. So if I was to draw all my field lines in isolation, I would draw them all coming in from different points. And if this is next to a positive charge, you can see that this line's going to move away from K and towards L. Okay, so it's going to go directly from K to L. And so I can draw these lines kind of curving like so. They would come in like this. Okay, there we go. So I can finish them off coming from in towards L. They're going to be sort of like this. Okay, and I'm going to do the same over here with M, just really quickly. Oops, not very good lines, not very good arrows, but you get the point. Okay, here they are. Now, M is a positive, L is a negative, so this is going to go straight towards there, and then these lines are going to curve. Like so. And if we finish off with a few green arrows just coming in, there we go. Now, I mentioned flux, we don't need to worry about that, but just to mention it because it's kind of interesting, K and M have different values. K has a greater concentration of electric charge, so it would have what we would call a higher flux or greater flux of field lines. So if I was being really good at this, I would draw more of them, okay, or bigger arrows to represent this greater charge. But that's why this wording is sort of loose. It's saying mostly, because these field lines are more dense, they have a greater flux, we would expect there to be just a tiny bit more of a curve towards the stronger field lines, but it would be pretty mild. So hopefully you can see at point P, these field lines are going mostly down. Okay, and that's really important for our answer. So mostly down means that we can hopefully get our answer. It's going to be D towards the bottom of the page.